Thank you for that kind introduction. And I would like to begin by thanking, of course, the organizing committee for inviting me. Also for accommodating my vegan needs. Thank you so much for that. It's always delightful to visit Mainz. And today I want to start with actually a couple of questions for you guys. So how many of you think that we humans are energy efficient? Raise your hand if you think that we are energy efficient. OK, let's see a few hands. How many of you think that we are going through an energy crisis? OK, let's see hands. 2 hands. So let me share with you a thought-provoking quote from a visionary American architect, Richard Buckminster Fuller. He said, there's no energy crisis, only a crisis of ignorance. And I think that if I think of me as a human being, this concerns me. But as a scientist, it makes me want to take action. And I think we should all keep this in mind in our research to try to fight against this crisis of ignorance to improve our energy efficiency. And now I will move on to the science. So I will begin by introducing magnetic skyrmions. So these are spin configurations with an integer topological charge. And I will use the example of a ferromagnetic skyrmion to explain this in a bit more detail. And the texture of a ferromagnetic skyrmion is shown on the left. There's a well-defined core, and at the center of which there's a spin pointing downward. And as you move radially outward, the spins are rotating and then eventually point upward. So what's topological about this texture? If you bring all the spins to the origin, you end up with the figure on the right. The spins are pointing in all directions, covering the unit sphere. And the number of times that the texture covers the unit sphere is a topological invariant called a topological charge. In the case of this example, this ferromagnetic skyrmion, the texture of which covers the unit sphere 1 time, meaning that it has a topological charge of magnitude 1. Magnetic skyrmions have been observed experimentally in bulk chiral magnets using neutron scattering. But that was not enough. So then they performed Lorentz transmission electron microscopy to reveal their structure in real space in thin films of chiral magnets. They have also been detected experimentally in nanowires using cantilever magnetometry. And finally, they were also experimentally observed in ferromagnetic ultra-thin films using spin-polarized scanning tunneling microscopy. So for those 4 cases, really low temperatures were required. However, fairly recently, magnetic multilayers have been shown to host skyrmions even at room temperature. So now it's time for me to give you the mandatory skyrmion sales pitch. Due to their topological nanoscopic size, enhanced stability due to their topological charge, and efficient coupling to electromagnetic fields, magnetic skyrmions have been suggested as promising candidates as information carriers in future magnetic storage and logic devices. So there's been a lot of focus in this field on the topological properties from the texture in real space. And the case in point is shown here between the interplay of electrons and the magnetic texture of skyrmions. So when electrons traverse a magnetic skyrmion texture, they feel the presence of the emergent magnetic field from the texture, and thus they get deflected because of the Lorentz force. And that gives rise to the topological Hall effect of electrons. But at the same time, the electrons exert a torque on skyrmions, making the skyrmions themselves get deflected. And that gives rise to the Skyrmion Hall effect. And these 2 effects, these 2 Hall effects have been measured experimentally. So on the right, on the left, I'm showing the experimental signature of the Hall resistivity that has a non-zero contribution from this topological Hall effect of electrons only in the temperature and magnetic field regions where skyrmions are present. And on the right, I'm showing you the experiment where using an electric current pointing to the right, it moves skyrmions, but they also get deflected as predicted by this Skyrmion Hall effect. So as I said, driven by this topology in real space, I also participated in producing some work on these lines. And I focused on the quantum nucleation of skyrmions, on controlling the skyrmion helicity, and also on the effect of disorder on the collective dynamics of driven skyrmions. So this is important to work on, but nowadays we are trying to change to a new direction to see how else we can use skyrmions. And for that, I will briefly introduce the field of Magnonics. Magnonics is a field of science that studies how to transport and how to encode information in spin waves. And spin waves are collective modes of the magnetization field. It's called Magnonics because the quanta of spin waves are called magnons. And one of the most important things about this field is that because there's no displacement of electronic current of electrons, there's no Joule heating. In this field, there's been a lot of research, and there have been proposals of devices that use magnons, such as a Magnon transistor or a Magnon interferometer. Those two could be building blocks to construct logic gates. But also there's been proposals fairly recently to take advantage of the spin wave nature, of the wave nature of spin waves, and in less conventional devices like this one that I'm showing at the bottom, that uses the interference of spin waves to resolve the spectrum of a signal. So to transport spin waves, to study the transport of spin waves, there's been a lot of research on how to realize that using Magnonic crystals. And Magnonic crystals are engineered pattern, sometimes, systems with a spatial modulation of the magnetic properties. And you could have, for example, a periodic arrangement of nanostripes, or a slab with inclusions of a different material, or holes. And those would modulate the spin waves, giving rise to spin wave bands because of the periodicity in space, band gaps, and things we're used to from electronics. These are systems that, as I said, focus on transport of spin waves, how to control the transport of spin waves. And one of the things that in this field is the most challenging is how to control the directionality of the Magnon spin currents that could be potentially used in applications. And there's been proposals to do that, but unfortunately, those proposals require an electric current to change the magnetization field. And as I mentioned before, we would like to avoid having an electric current because that is producing Joule heating, dissipating energy. So to try to improve on that, there's recently been the proposal to use topological Magnon insulators. And topological Magnon insulators are systems with a spatially periodic magnetic texture that can support topologically protected Magnonic edge states. They are the analog of electronic topological insulators, but for magnons. And they could be either engineered, as in the Magnonic Crystal proposal I'm showing on the left, or they could be realized in compounds, as in the prediction of the study on the right. Those Magnonic edge states that they support, they are robust unidirectional channels for Magnon spin currents that could be used in spintronic applications. And we have in mind applications that utilize electrically insulating magnets, because as I pointed out, we would like to get rid of Joule heating. So in my talk, I would like to make the case that Skyrmion crystals are interesting topological Magnon insulators where we could realize these ideas, to have robust unidirectional channels for Magnon spin currents that we can control. So I'll start with published work on antiferromagnetic Skyrmion crystals. This is the texture of an antiferromagnetic Skyrmion crystal. We are very excited about this publication because we made it to the cover of PRL. And a funny story, when I first was contacted about getting one of our figures as a cover, my first reaction was, great, more exposure for our work. But my second reaction was, PRL has a cover? Who looks at that? Here you have an example. So let me enlarge it a bit so you can see the texture better. And the first thing that I want to point out is that those spins are on a triangular lattice. This is a texture which is the classical ground state of the following Hamiltonian. It has just 3 terms from left to right. There's antiferromagnetic exchange interaction. Then there's, and of course, that favors the neighboring spins point in opposite directions to each other. Then I have an interfacial Jeloshinsky-Marine interaction that favors neighboring spins to form a relative angle with each other. And finally, there's a coupling to an external magnetic field that's pointing out of the projection towards you that favors alignment along the magnetic field direction. So as I said, this crystal is a spatially periodic texture. It has a magnetic unit cell. It's a single antiferromagnetic Skyrmion. It has a topological charge of -1. And the texture itself is a triangular crystal of antiferromagnetic Skyrmions. A noteworthy fact is that this texture has a tripartite structure, meaning that it's comprised of 3 interpenetrating sublattices, each of which has the texture of a ferromagnetic Skyrmion. But I am not just merely interested in the texture. I want to study the Magnonic excitations. So we did that, and we found the following. So I am here showing you the Magnonic band structure and labeling each band with this little yellow box is the Chern number, which is a topological invariant in reciprocal space. What's remarkable about this is that the lowest energy band is topologically non-trivial. It has a Chern number of +1. That means that the band gap right above it, the first Magnonic gap highlighted in green there, should be hosting a topologically protected Magnonic edge state. That comes from intuition or guidance from the bulk edge correspondence. And we know that this is not an established theorem. So we would like to check that this is indeed correct. And we do that by putting our system that was just bulk now on a strip with edges. Here I'm showing you the texture that ends up appearing, where the top and bottom there are the edges of the strip. And this is a infinitely extended strip. It's along the horizontal. The edges are just where the sample terminates. That's it. And highlighted in yellow there is the new magnetic unit cell. So when we compute the band structure for this system, we indeed find that in the first Magnon gap, 2 states emerge. They're colored in blue and red. So the blue the blue state, the blue mode, has a positive slope, meaning that it's propagating to the right, and the red one has a negative slope, meaning it's propagating to the left. We checked their wave function, and we obtained that they are indeed localized at the edges. So the blue one is localized at the top edge, the red one at the bottom. So these are chiral Magnonic edge states. Why 2? So because we use an infinitely long strip, we are going to have one at the top and at the bottom. But if we had a finite size system, these two would merge into a single one that would be propagating clockwise along the boundary of the system. And as promised, here I'm showing the Magnon spin density. It's indeed localized at the edges, which supports this idea that we have that these are the unidirectional channels, robust unidirectional channels for Magnon spin currents. It's important to stress that because this emerges at the first Magnon gap, that's where the lifetime of Magnons is the longest, and that's where our approximations work best. So I would like to propose an experiment to measure this. It goes like this. So first, we need to realize this antiferromagnetic Skyrmion crystal texture. So to do that, we first could use materials that are known to be arranged in a triangular lattice with antiferromagnetic interactions. That would be the green slab. And to induce interfacial DMI, we could have a bottom layer with a heavy atom system. And then we have the external magnetic field. So if you do that, and you get your texture, you have your sample, you know that the edge states are going to emerge only in the band gap that I discussed. So using, let's say, some ferromagnetic resonance technique, you excite only within that gap, then you're going to excite only those edge states, and you should be able to detect that using like a local probe or a global probe like BLS, brilliant light scattering, to detect only a Magnonic signal at the edge. But if you tune this window of excitation a little bit above where the bulk states are, or below the gap, then you would observe a signal all across the sample. So to conclude this first part, I showed you that there's a robust antiferromagnetic Skyrmion crystal where its first Magnon gap is topological, which means it hosts a topologically protected chiral Magnonic edge state at the lowest energy that we could have it, and that the experimental prediction here is that you should be able to detect Magnons at the edge. Now I will take you into an uncharted territory because this is unpublished results. And I will be talking about now a ferromagnetic Skyrmion crystal. That's the texture. It's also a triangular crystal of, in this case, ferromagnetic Skyrmions. The way we obtain this texture is using basically the same spin lattice Hamiltonian I introduced before. The only difference is that now there's ferromagnetic exchange interaction. So long story short, we do compute the bulk band structure. Looks like that. That's extremely boring and featureless, and I like colors. So what I do is always I add colors. So you notice those purple, almost flat bands. Those are indeed associated with localized modes of each ferromagnetic Skyrmion. And from lower to higher energy, they correspond to modes with different azimuthal angle. So an elliptical distortion first, then a triangular, square, pentagonal. And these are observed for not only k equals 0, not only at the gamma point, but also at non-zero k values in reciprocal space. But that's not the only thing that we can observe here. So here I'm labeling with A, B, and C, the anticlockwise, the breathing, and the clockwise modes. They have been studied quite a lot in ferromagnetic Skyrmion crystals. And they look like that. So ABC in that order. What I want to point out about these is that if we now study what happens as a function of the magnetic field, when you increase the magnetic field and you track what happens to each of those modes, this is the picture that emerges. So those nearly flat bands that I discussed, they are shifted upward in energy. And even though when they cross the other bands that are more bent, they remain almost intact. These nearly flat bands have no turn number. They are topologically trivial. And when they go through those other bands, nothing happens. Even though you see gaps closing, it's as if they were completely decoupled from the others. A different story happens with those anticlockwise and breathing mode. So there I'm highlighting the trend as you increase the magnetic field of those two modes. So you see how they get their energy difference becomes smaller and smaller. Now the plot thickens because this is something that they have observed experimentally as well. So using magnetic resonance in a bulk system, they also detected that in the Skyrmion crystal phase, those modes were getting smaller. The energy difference of those modes were getting smaller and smaller in energy. But in that case, in that system, the bulk system, they don't quite get to match their energy because the transition to the conical phase stopped them. But our model is better suited to describe thin films. So we can push it further. And what we observe is the following. If we keep increasing the magnetic field, there's a critical field at which the gap closes, this gap that is defined by the anticlockwise and the breathing mode. And then it reopens for higher fields, higher than this critical one. So in terms of the turn numbers, this is the picture that you should have. So the first and second band have trivial topology, 0 turn number. But the band that has the anticlockwise mode has a turn number of +1. And the one with the breathing mode as well. So when we go through this critical field, those lower energy bands remain at 0 turn number. But there's a transfer of turn number from the third to the fourth band. And that, of course, could have been guessed maybe from the fact that the anticlockwise and the breathing mode got inverted. So this is meaningful because it tells us that, using the bulk edge correspondence, that in the case on the left, you should expect a chiral Magnonic edge state in the third gap. And we call that the topological phase. But in the rightmost case, because of the turn number transference, you would lose that chiral Magnonic edge state in that band gap. So we checked this, again, using a strip geometry. And we confirm that in the topological phase, below the critical field, we do see those chiral Magnonic edge states. They are robust against disorder. We include disorder near the edges, and they remain there. So I'm talking about those blue and red states in the third gap. Okay. And in the trivial phase, even though there are edge states, those are trivial. We can remove them by disorder, which is what I'm showing in this slide. So to conclude the second part, there are nearly flat bands in the spectrum of ferromagnetic Skyrmion crystals. Those are those localized modes that we observed, and they carry 0 turn number. But there's a topological phase transition in the spectrum of spin waves that we can control and tune with the external magnetic field. And this is going to give us a further handle on the edge states for the system. And we have this potential prediction that this could be observed in thin films of a system that hosts Skyrmion crystals, for example, copper oxide selenide. So to conclude, I think I convinced you, I hope, that Skyrmion crystals, both ferromagnetic and antiferromagnetic, could be potentially useful in topological magnonics because of these robust unidirectional channels for Magnon spin currents. Thank you.